So these ones, there's not much memorization to do here, right? Are these pretty easy? Pretty easy. You should know the name of the elements, and then when we look at the ions, these are all what? Alkali metals, group 1. These are all alkaline earths, group 2. So this is group 1, group 2. Aluminum is group 3. And so we can see what the charge is. However, there are some that are fixed charge that aren't as easy to remember. And it depends on what periodic table you use. I don't like this particular periodic table here compared to the old periodic tables. You know, there's been a switch to do this numbering convention from 1 to 18. Do you see that? But my preference is the old style with the Roman numerals. I much prefer that because it gives you a little bit more information. And so for something like zinc, what group is that in? If you look at the zinc ion, well, zinc, that's in group 12. In the new style of numbering. But in the old style of numbering, it's not in group 12. Do you know what group it is in the old style? Yes. Group 2. Let me see, what did I do with that? And so I prefer this style of periodic table. Unfortunately, this banner I can't get rid of. And so what I'm going to do instead is this. I'm just going to use their periodic table here. That's good. For my PowerPoint slide here. And so we actually have two group 2s. And the first group 2 we'll just call 2A. That's the alkaline earths. And then we have a second group 2. These are the pseudo group 2s. Like the alkaline earths, these also have a plus what charge? Plus 2 charge. And so the pseudo group 2 will be plus 2. And then these are the pseudo group 1. And so we know group 1A over here. I don't know what happened with this. This is 11A, so this is a typo. But group 1A over here should have a plus 1 charge. How about pseudo group 1? This should also have a plus 1 charge. But these are rules. These aren't laws. And so they're exceptions to rules. And so, for example, some of these, there are no exceptions. Zinc, you know what the charge on zinc is? It's always plus 2. There's no exception. If we have a zinc ion, it's plus 2. Cadmium, there's no exception there. It's always plus 2. However, copper is not always plus 2. Do you know what copper is? Plus 1 and plus 2. Actually. And so copper is a little weird because it should only be plus 1, not plus 2, plus 1. And but it's also plus 2. Silver is only plus 1. And so I like this. Aluminum is going to be plus 3. But what about this? This is 3A. We have another group 3 down here. This other group 3 we're going to call 3B. And so scandium, you know what scandium is always? it's always +3. Yttrium is always +3. Therefore, titanium should always be +4, except it's difficult to it's difficult to lose 4 electrons, because each electron you take, it becomes increasingly more and more difficult to do what we call ionize or remove the electrons. And so titanium has variable charge. Probably the most common charge on titanium is +4, but not as a free ion. We see titanium +4 in compounds, so that +4 charge is stabilized by things like oxygen. And so one of the most common compounds around is TiO2. TiO2 is titanium fluoroxide. And titanium fluoroxide is used as a white pigment in paint. And so this is the old white, actually this is the new white pigment. Do you know what the old white pigment is? The old white pigment is another group 4, but this is not group 4B, this is group 4A, and it is lead. Lead 4 oxide used to be the old white pigment in paint. And the problem with that is lead poisoning, so they don't use lead 4 oxide as the white pigment anymore. They usually use titanium dioxide, but now there's some other pigment in paint, which gives an even whiter white. And the even whiter white, it reflects more of the sunlight. And so they have some kind of paint that reflects like 99.999% of the sunlight and looks extremely white. And that, they're looking at painting the tops of buildings to keep them cooler, or the tops of automobiles to keep them cooler too. But I don't think it's titanium 4 oxide that they're using. Vanadium should be plus what? +5. Now you aren't going to see any +5 free ions, but you'll see vanadium as a +5 in many compounds. And so that's what we call the maximum. And so these numbers here in the Roman numeral are something called the maximum oxidation state. Do you guys remember oxidation state and oxidation numbers? Yeah? Those are the maximum oxidation states. So the max oxidation state for chromium is +6, but it isn't easy to lose 6 electrons. And so a lot of these, what they do instead, losing 6 electrons is pretty tough. Most of these, it's easy to lose 2 electrons, because the 2 electrons that are lost are the s electrons here. And so those are easy to lose. And then maybe a third electron. A third electron is not going to require too much. And so +3 cations are fairly common, but what about +4? No, +4 are pretty rare. There are some, for example, lead 4 ion, and what's this, SN? Tin 4 ion, those are common. Lead 4 and tin 4. But those are pretty big, and so it makes it easier to lose. But something like vanadium or chromium, these are quite small, and it's difficult to lose. And therefore, +2 and +3 are common. +2 for sure, +3 for some of these, yeah. And so these ones will have variable charge, +2 and +3 in this area. But when we get to pseudo group 1 and pseudo group 2, then you got to know that copper is +1, +2, silver is only +1, gold is +1, +3. Okay, you don't need to know gold, but for sure you should know copper, 1 and 2, and silver, fixed. Zinc is fixed at +2, cadmium is fixed at +2. What about mercury? Mercury is +1 and +2. Over here, if we go from this group 4, it's hard to lose all 4. The same thing over here. Aluminum should be +3, and boron should be +3. Carbon should be +4, and that would be its max. But as a stable ion, it would be too reactive. So carbon is quite small. With a full +4 charge, would be highly reactive. So it's not very stable. But there's ways to stabilize it. One way of stabilizing it is to bond oxygens to it, and that helps stabilize it. Nitrogen should be +5, but for species like carbon and nitrogen, we're going to see a lot of different. Maybe we aren't going to lose a full 5. So for example, +2 is common for carbon. And then for nitrogen, we'll have +1, +2, +3, +4, +5. Oxygen should be at +6. Fluorine should be at +7. And these, +8. But you aren't going to expect the noble gases to lose any electrons. Right? And so we're going to reach a tipping point. The tipping point is here at carbon. At carbon, you know, we could either lose 4 electrons or gain 4. And do you guys remember being isoelectronic with noble gases here? Yeah? No? And so if carbon loses 4 electrons, we're at 2 electrons like helium. If carbon gains 4 electrons, then we're at 10 electrons like neon. Now it's hard to gain 4 electrons fully, but if carbon, we're able to gain 4 electrons, then we form C4 minus. Do you know the name of C4 minus? Carbon with a 4 minus charge? How about this? If oxygen could either lose or can gain, and in this case it'd probably be easier to gain. If oxygen gained 2 electrons, it would be isoelectronic with neon, and we call it O2 minus, and that's called what? O2 minus. Oxide, and F would probably want to gain 1, and we would call that fluoride. Nitrogen would want to gain 3, we call it nitride. And so we can get the charges off the periodic table here. And so that's going to save us some memorization. So this is group 1, group 2, group 3, group pseudo 2, group pseudo 1. These are kind of in the middle, easy to lose 2 and maybe a third. And so +2, +3 are common, but the max charge on chromium can go all the way to +6. We just don't see it as a monatomic ion. It has to be bonded to oxygen. So for example, chromate. In chromate, chromium is +6. In dichromate, chromium is +6, but it's not chromium alone. It's chromium either with 4 oxygens or with 7 oxygens. You know, 2 chromium and 7 oxygens, dichromate. Iron 2, iron 3, it's going to max out here, but the max charge on iron is +8. Cobalt here, same thing, +2, +3. So we're kind of in the middle of the periodic table, it's +2, +3. And then we have our pseudos here. This is pseudo group 1. This is a +1, +2. This is pseudo group 2. And this is +1, +2. This is mercury 1. Do you guys remember mercury 1, Hg2, 2+? So like a molecular ion. And this is tin. Tin is not in group 2. You know what tin is? Tin is in group 4. And so we need to do that. Tin is not fixed charge. You can tell because they're using a Roman numeral there, but another common tin ion is tin Roman numeral 4, or the tin 4 ion. This is going to be SN4+. And then lead is also group 4. And so the other common lead ion is lead 4, which would be Pb4+. So having a charge of 4+ alone makes it a little bit more reactive, or quite a bit. So for example, if we go to cadmium 4+, that becomes extremely reactive as a single ion, but there are ways to stabilize this. Right. On the other hand, we can gain. You know, if we're further to the right, it's easier to gain than to lose. So here we have our fluoride, oxide, nitride, and some of the others. So do you guys remember doing those pretty much? Yeah. All right, the next thing we're going to look at are the polyatomic. So those are the monatomic. The monatomic cations are pretty easy. If it's fixed charge, you don't need a Roman numeral. If it's variable charge, you need a Roman numeral. And if it's an anion, you add the "ide" ending. So I'm assuming this is mostly review. Okay. I'm sorry? Polyatomic, yes. All right, so how's your progress with the memorization going? Good. All right, how about somebody tell me borate? What's the formula? Borate is BO3 3-. And one thing that helps helps me to remember this formula is the group. What group is boron in? Boron is in group 3A. And so the way I remember this is it's 3, 3, 3. That's borate. How about silicate? Do you have that one memorized already? No. What is it? It's SiO4, not 2-. 4-, yeah. SiO4 4-. And one way I remember this one is, what group is silicon in? It's in group 4. 4A, and therefore it's a 4, 4, 4. Do you see that? So it's easy to remember. And then these other ones you don't have to memorize because there's a pattern to it. Do you know the pattern? So, well, what is carbonate? Do you have that one already memorized? Most people do have carbonate memorized. Yeah, CO3 2-. Nitrate. Try to. Nitrate is NO3-. Good. There's no oxate. Fluorate. Fluorate is FO. When you have a T here, that means it's an oxyanion.
What does that mean?
It contains oxygen. And anion means it's negatively charged. We just need to know how many oxygens. Take a guess how many oxygens fluorate has. 3. Take a guess what the charge is. Negative. We can't go any smaller. Do you see a pattern here? Chlorate. Oh, well, I keep fluorate in here for the pattern. Fluorate is too unstable. Doesn't really exist, but chlorate's quite stable. What is the formula for chlorate? ClO3-. That's chlorate. Bromate. BrO3 charge minus. Iodate. IO3-. All right, do you see a pattern there? And so if you recognize a pattern, then one, it makes remembering these easier, right? If you recognize a pattern, then you can derive it. There's oxalate, right? But this is is there an element named oxonium or oxinium? No. And so these are oxyanions. These are oxyanions, and so it would have to be an oxygenate, you know, based on the element. And so there is no 8 for oxygen because it would be an oxygenate. But oxalate is something completely different. And that's something that doesn't fit this pattern. If this pattern were perfect, we can call it a law, but otherwise we just call these rules of nomenclature. Rules can have a lot more exceptions.
What is silicate's charge?
4 minus.
Thank you.
Narrow this down. All right, there's an outer pattern with these, and then there's an inner pattern. So let's take a look at the inner pattern here, starting with silicate. Okay, if silicate is SiO4 4 minus, what would you guess phosphate is? PO. Yeah, 3 minus is the correct charge. And how many oxygens? 4. PO4 3 minus. That's phosphate. Sulfate is SO4 2 minus. Good. How about selenate? SeO4 2 minus. Tellurate. TeO4 2 minus is correct. How about arsenate? ASO4 3 minus. Antinomate. Actually, let's skip that one. It's difficult to say. How about germinate? GeO4 4 minus. All right, so do you see a pattern there? Yeah. And so number one, patterns will help ease your memorization load. Number two, if you memorize these with flashcards, could you predict it? So let's say you didn't make a flashcard for arsenate, and all you knew were the flashcards. Could you make a prediction? No, you couldn't make any prediction because you didn't have that flashcard. So either you knew it or you didn't. But if you know a pattern, then you can try to make a prediction based on the pattern. You know, it's not always correct, but at least we have a chance of getting it. There's additional patterns in here that I'd like to talk about as well. And you know, through geologic time, the atmosphere's changed. You know, back in certain periods, the atmosphere didn't have nearly as much oxygen in there. There's a lot less oxygen. And in fact, the atmosphere was what we call a reducing atmosphere. A reducing atmosphere doesn't have much oxygen. And then if you have like iron, you could have iron that doesn't rust, because if there's no oxygen, well, is iron going to rust? No, so you'll get iron deposits. But then as the atmosphere changes and it becomes more of an oxidizing atmosphere, you have more oxygen. What does oxygen like to do? Oxygen likes to oxidize things. And what is oxidation? Taking electrons. So oxygen likes to take electrons from things like metals, like iron. So we go from iron, you know, to iron plus 2, that's a common charge. So we could form iron 2 oxide, but ultimately we'd probably form iron 3 oxide. But iron 3 oxide is not its max, but it's pretty much the max oxygen can do. In order to go to iron 4, 5, 6, you'd need something more powerful than oxygen. Oxygen just isn't going to get you there. And so iron, it pretty much stops at iron 3 oxide, and iron 3 oxide is what we call rust. Right? And so we live in an oxidizing environment, so things have been oxidized to its max, you know, because we have, what, about 20%, 21% oxygen in the air here. And so if we have carbon, you know, it's hard to find carbon deposits. Like I think in Alabama, they have this place where you can go looking for diamonds, and some people have found kind of big diamonds there. But are diamonds all that common?
Yes.
Well, compared to, let's say, carbonates. You know, when I was in geology, we would have a belt, and on the belt there's a little hook, and on the hook you put, you know, those squirt bottles in the lab? You put a squirt bottle, but you don't put water, DI water in there. You put hydrochloric acid. So we had a bunch of squirt bottles with hydrochloric acid. Somebody asked me if the bottle had DI water. I said, you know, you never know what somebody puts in there. And so we had hydrochloric acid, and we'd go around squirting the rocks. And you can tell if the rock is a carbonate rock, because what would happen when the acid attacks the carbonate? Do you know what happens? When acid attacks carbonate, you form carbonic acid. Carbonic acid decomposes into CO2 and water, and you get effervescence. Remember, the effervescence is when you have the bubble formation. And so you're looking for effervescence. If it effervesces, then it's carbonate. What types of carbonate rocks? Like limestone, you know, is common carbonate, although there's not much limestone around here. You could have minerals like calcite, you know, limestone, calcite, or it could be like marble. You know, marble is a mix of calcium carbonate and magnesium carbonate. But most of the carbon has been oxidized, you know, unless you hit coal. You know, coal deposits, like underground and stuff, you might hit the coal deposit. And the coal deposit consists mostly of amorphous carbon. Have you heard of amorphous carbon? What's the difference, or what is amorphous? Do you know what amorphous is? Structureless. Have you heard? So we have two extremes. We have crystalline materials and amorphous materials. Crystalline materials have a very well-ordered arrangement, like diamonds. The carbon atoms are very well ordered, and you get very nice crystals. Whereas amorphous materials have a lot more disorder to it, and so they aren't so well ordered. So a lot of coal deposits is amorphous with some graphitic carbon. Unfortunately, graphite isn't such a big find like diamond would be. But anyway, there is some deposits, but what tends to happen in this oxidizing atmosphere is like that organic matter. You know, we have two types of carbon containing compounds. We have the inorganic and the organic. In the inorganic would be like carbonate, carbon dioxide, carbon monoxide, graphite, diamond. Those are inorganic materials. But the organic carbons, those are going to have like hydrogen bonded to it. And when we have hydrogen bonded to it, then it changes. It changes its oxidation state. And so typically what we have here is this. Carbon can either lose 4 electrons. If carbon loses 4 electrons to go like helium, then it's +4. On the positive end of the oxidation state spectrum, we have mostly inorganic compounds like carbonates, carbon dioxide, carbon monoxide. However, it can also gain electrons. It can gain up to 4 electrons to form something like carbide, but it doesn't have to form carbide. On the other end of the spectrum, on the negative end of the oxidation state spectrum, we have the organics. Now, it makes a big difference in the property. So let's say I had a torch. Do you think the limestone, I could catch it on fire with a torch? No, it's not going to catch on fire. And the reason it's not going to catch on fire is because the carbon has been completely oxidized. And so we need to review oxidation states and oxidation numbers. Do you know the oxidation state of carbon in carbonate? And so what we do here, and the rules, let me just show you the rules briefly. I have a much more compact set of rules for this. So I'm just going to go through these very quickly. The oxidation state of elements is 0. The oxidation state, the sum of the oxidation states of all the atoms in a compound or an ion have to add up to the net charge. The net charge might be 0 or the net charge might be non-zero. That's what this is saying. 3. We assign oxidation states in a certain order. And this order is important, otherwise we might make a mistake. So group 1 and group 2 get +1 and +2. In compounds, those are always +1 and +2. Hydrogen is always +1. Fluorine is -1. Hydrogen is usually +1. I shouldn't say always +1 because there's another hydrogen ion, and that's hydrogen with a -1 charge. So hydrogen with a +1 charge is called hydrogen ion. Hydrogen with a -1 charge is called hydride ion. And if we follow this sequence, then we'll know if we have hydrogen with +1 or the -1 because of the sum. And we're going to use the sum rule number 2 to help us figure it out. Number 6, oxygen is usually -2, but in some compounds, if we do hydrogen before oxygen, then sometimes oxygen is -1. So oxygen is -2 in oxides, but we might have a peroxide. If we have a peroxide, oxygen is -1. But going in this sequence, then we can tell if it's a peroxide or if it's an oxide. And then we can assign the rest here. This is for binary. For binary ones, I just assign the more electronegative one with its preferred charge. Okay, so let's go back to carbonate and take a look at the oxidation state here. So what we do is normally, we'll do group 1, group 2, oxygen, hydrogen. Actually, we do hydrogen before oxygen. So I do group 1, group 2. Well, there's no group 1, group 2. Then I do hydrogen, and there's no hydrogen. Then I'll do oxygen. And oxygen gets what its preferred charge is. So the preferred charge is oxygen can either gain 2 or it could lose 6. And so what do you think is going to be easier, gaining 2 or losing 6? Gaining 2. So the preferred charge on oxygen is -2. And so I do this like this when I sum it up. So I need to sum up the charges so that it equals a net charge. Now carbon can be anywhere from +4 to -4. I don't know where it is, so that's why I need to do this. So I have 3 oxygens at -2, plus 1 carbon at plus whatever. So x minus 6 must equal the net charge of -2. That's the net charge here. So what is x? X minus 6 has to equal -2. X must be +4. And so this carbon is +4. Well, +4 is at its limit. It can't go any higher than +4. That's it. Well, it could, but it'd be terribly unstable. And so that's its normal limit, +4. And so what we say is that this carbon with these oxygens the carbon is in its maximum oxidation state of +4. So if you have an oxidizer, what does an oxidizer want? Oxidizers want electrons. So if you're an oxidizer and you come along and you try to take more electrons from carbon, does carbon have any more electrons to give up? No, not in the valence shell, the core, but the core unreactive. Then oxygen starts looking around. Well, if you can't take it from carbon, can it take it from these oxygens? These oxygens are -2, so if an oxygen comes along and there's a tug of war, oxygen versus oxygen, what's going to happen? Nothing. So this is what we call oxidized. So the 8s typically have the element completely oxidized. And so carbonate, the carbon's been completely oxidized, +4. How about borate? What's the oxidation state of boron in borate? So this is -2 times 3 is -6. X minus 6 has got to equal -3. X must be +3. So do you see that? So the borate is max, carbonate's max. How about nitrate? Here, I'll do nitrate. Nitrate's very common. So we'll just do it pictorially again. So nitrogen versus oxygen, nitrogen is going to go first, or no, oxygen. Well, oxygen is going to go first. Why? Because it's more electronegative. So that's a rule, not written there, but you can use. And then we have one nitrogen at +X. And so X minus 6 is equal to the net charge of -1. And so it's got to be +5. So even if the atmosphere increased in oxygen, we're at 21% oxygen, but let's say in the future, some geologic event happens and then oxygen goes up. Actually, the oxygen, when did the oxygen start appearing? Oxygen started appearing when the plants, right, and trees and that. So let's say somebody has a tree planting campaign because maybe plant more trees, get rid of CO2 because trees take the CO2 and then convert that into O2. And let's say the oxygen levels increase. Say we're at 23%, 24%. So it becomes more and more of an oxidizing environment. As the oxidizing environment increases, are we going to oxidize these any further? Or have these maxed out? They've maxed out. And so historically, these are the species that chemists found, and this is why they're called the eights. Borate, carbonate, nitrate, because those have maxed out. How about, let's do one of these. Phosphate. We just did nitrogen was +5, right? What is phosphorus in phosphate? So we have 4 oxygens, -2 each. 4 times -2 is -8. -8 plus what gives us -3? +5. So phosphate is maxed out, correct? Maxed out. If we go to sulfate, this is -2 times 4 is -8 plus what gives us -2? +6. This is group 6, it's maxed out. Now we go over here, and we go to chlorate. So it's -2 for the oxygen times 3. So that's -6 plus what gives us -1? +5. Is chlorine maxed out? No. Chlorine's maxed out. It's not maxed out. And so our nomenclature has to be modified a little bit. Because since it's not maxed out, we're going to need to max it out. And that is, this is called chlorate. And then we have something called hyper. Do you know the prefixes hyper and hypo? Hyper means what and hypo means what? Yeah, more. Hypo means less. So a lot of people who go camping worry about hypothermia, freezing to death. But on the other hand, there's hyperthermia. Did you hear about the motorcyclists going through Death Valley this summer? I think 2 of them died or something. 135 degrees.
I felt like that today on my way to school in the weather. It's awful. Because 80 degrees, you think wind chill helps, it doesn't.
Yeah, yeah. That's tough. There's no AC on the motorcycle, huh?
There's no AC on the motorcycle. It's
Yeah,
terrible.
that's terrible. Well, unfortunately, these guys had heat stroke, and so anyway, we're going to have hyperchlorate, but hyperchlorate's too long, so we're going to shorten it to what? Yeah, perchlorate, because it's not maxed out. And so, you know, under the maybe if the level of oxygen increased, we're at 21% oxygen now. But if the level of oxygen kept increasing, maybe hyper or perchlorate would be the common one that's found rather than chlorate as far as salts go. So chlorate salts you can find, but perchlorates you got to make them because they don't occur naturally. Does that make sense? And actually, perchlorate, what's the formula for perchlorate? The formula for perchlorate is ClO4 minus. And so let's look at the oxidation state for perchlorate. The oxidation state of chlorine in perchlorate is, okay, 4 times minus 2 on oxygen gives us minus 8. Minus 8 plus what gives us minus 1? Plus 7. So perchlorate's maxed out. We're not going to have hyperchlorate. It's just going to be perchlorate. Okay, let me ask you this. If you know patterns, then you can make predictions. And this is much more powerful than memorizing flashcards. So for example, if I asked you, does persulfate exist? What would you tell me? No. Although, you know, you got to recall that these are rules. And there could be a persulfate, but it's not what you think. You know, you would think a persulfate would be the next higher oxidation state, but they have a persulfate because there's a peroxide bond in there. So even though they call it persulfate, it's not a persulfate like this. It's a persulfate because there's a peroxide. Does that kind of make sense? And so these are rules, so you don't take them too, because nomenclature is always, you know, there's people debating about how things should be named, and there's changes with that. But sulfate analog of perchlorate does not exist. How about percarbonate? Do you think percarbonate would exist? No. It wouldn't, because it's already maxed out. We can't go higher than plus 4. Plus 4 is its max. Okay, so if we know some patterns, we can make predictions for things we haven't seen, and hopefully those predictions turn out to be accurate. Some of these, though, you just have to outright memorize. You know, so I gave you the ones that we have to outright memorize, the ones with the 8s. And the ones with the 8s that we had to memorize were chromate, dichromate, etc., oxalate. Those don't fit a simple pattern. And so however you memorize those, do that. What I found to be effective for memorization is just writing it, you know, because it's like, you know, initially when you like learn how to ride a bicycle, it's pretty tough, and you have to use a lot of brain power to think about how to stay balanced and that kind of stuff. But after a while, it's like you don't even have to think about it. You can just jump on and go. Well, it's the same thing. The way I memorize these is I try to get it into my motor memory. And so I'll just write it over and over, write it down on paper, like 50, 100, 200, 300 times. And pretty soon it's in your motor memory, so you don't have to use any brain power, you just rely on motor memory, you know, how to pedal or whatever else. Okay, there's some more that you have to memorize, and so let's talk about the others that we're going to have to memorize. I'm sorry?
I'm buying myself that. So I love rote memorization.
Okay. Let's look at some others that need to be memorized. Most ides are monatomic anions. You know, hydride, fluoride, etc. Monatomic anions. But there are some ides that are polyatomic anions. What are the ides that are polyatomic anions that don't fit this pattern on the periodic table? Sorry? Cyanide. What's the formula for cyanide? Cn minus. So that's one that doesn't fit the pattern. And so that would be a rule breaker there. What else? Peroxide. Peroxide is O2 2 minus. So each oxygen has an oxidation state or oxidation number of -1. That's peroxide. And which? Amide, which would be the ammonia analog. But amide, we'll talk about that later. Amide, you don't have to memorize it. There's one more that you should memorize for sure, and that is hydroxide. All right, when we have a D usually indicates it's monatomic anion, except for these three here, or four if you include amide. There are more. You know, again, these are rules. A T indicates an oxyanion, but we also have the ites. And so the ites, I don't bother memorizing. No, because the ites are easy.
Oh.
What are the ites? Yes, sulfite. But there's a pattern with the ites. Do you already know the pattern, or you don't know the pattern with the ites? Yeah, exactly. That's it. And so here's the pattern. We start off with the 8s, and then we had the per 8. So per prefix 8, this is the hyper. And so this is +1 oxygen. Same charge. In the ites, I don't bother memorizing because the ites are going to be -1 oxygen, same charge. So if you know that nitrate is NO3 minus, then nitrite must be NO2 minus, one less oxygen. But on the opposite end of the spectrum, you know, hyper is at the top, hypo is at the bottom. And so we're going to have the hypoites. Minus another oxygen. Same charge. Not everything will show the full spectrum. Chlorate does. And so perchlorate is ClO4 minus. Chlorate is ClO3 minus. Chlorite is ClO2 minus. And hypochlorite is ClO minus. And so this shows the full spectrum. But a lot of them won't have a per, and some of them won't have a hypo, and some of them won't even have an ite. But the 8s are there. So naming ionic compounds, we just name them according to the name of the cation plus the name of the anion. So sodium chloride, this one magnesium iodide. But we don't use the prefixes, the numerical prefixes. So we wouldn't call this one magnesium diiodide. Do you know why? We don't need to, because we would know the charge. Magnesium is group 2, so it's +2. Iodide is 1 shy, so it's -1. So we would know the ratio. And so if we have magnesium iodide, we know it has to occur in a 1-to-2 ratio. Aluminum is +3, oxygen is -2. So to balance out the charge, compounds have to be electrically neutral, it's going to be 2 aluminum, 3 oxygen. We know that. These are fixed charged. When we have variable charge, it's the same type of deal. And so here, we could have this one. What would this one be called? Now, variable charge is going to have 2 possibilities. So let's look at iron, FeO, and then we're going to have Fe2O3. So the first iron oxide is going to be called what? Iron, Roman numeral 2, oxide. And the second iron is going to be called iron compound, iron, Roman numeral 3, oxide. So we can differentiate. So variable charge here, we don't indicate. If I have iron in the +3 state, then in order to balance out the charges, I'll need 2 irons and 3 oxides to balance out. If I have iron in the +2 state, I'll need 1 to balance the charges out. But there are a lot of variable charge species in the periodic table. What are some of the other variable charge species in the periodic table? Well, all these are variable charge, but there are more. And so the others have to deal with these guys here. The max charge on nitrogen was +5 on the positive end and -3 on the negative end. But you know, sometimes it's hard to lose all 5, so we might form nitrite instead. The oxidation state of nitrogen and nitrite is different. It has a different charge. And so we see this especially in these types of compounds here. These are what we call binary molecular compounds. Now, molecular compounds form molecules, and typically compounds that are formed just from elements, typically those are molecular. Not always. This is a rule, not a law. And so when we look at this, look at how many different nitrogen species there are. So if you oxidize nitrogen, you have the potential of oxidizing it a little bit or oxidizing it a lot more. And so let's look at the oxidation states of some of these species here. So let's look at NO. We call NO nitrogen monoxide. Here we have to use the mono because we might have dioxide unless we use the charge. You know, there are 2 ways to name this. One, name it using the prefix nitrogen monoxide, mono being 1. Nitrogen dioxide, di being 2. Or we use a charge to name this. And so what is the charge on nitrogen here? Plus. Can you figure out the charge on this? It's plus. Well, what is oxygen? Oxygen is -2. -2 plus what gives us 0? It's got to be +2. So this is nitrogen. So another way of naming this is nitrogen Roman numeral 2 oxide. And then we wouldn't have to use the prefixes here. This is nitrogen dioxide. What's the charge on nitrogen in nitrogen dioxide? +4. So we could call this nitrogen Roman numeral 4 oxide. That way we don't have to call it dioxide, because if we have a nitrogen +4, then we're going to need 2 oxides to balance out the charge. And so there are 2 ways of naming that, but for the rules, we will name molecular compounds using this method. So nitrogen dioxide. We could do the same thing here. With iron, we could call it, you know, if we didn't know the Roman numeral here, or if we omit the Roman numeral, we could call this iron monoxide. Just one iron, one oxygen. We get rid of that. If we know the Roman numeral, then we don't have to use the prefixes because we know it has to be in a 1-to-1 ratio. Plus 2 minus 2. Here we could call this diiron trioxide or iron 3 oxide. Okay? But we don't want to mix it up. So for example, we'd never call this diiron 3 trioxide. Because if we did that, then we're giving redundant information, which means that we're wasting space. All right, so let's take a look. These are rules for binary molecular compounds. What's this one called? Dinitrogen monoxide, or nitrous oxide. This one? Oh, actually, before we do that, what's the oxidation state of nitrogen here? +1. This one's called dinitrogen trioxide. Oxidation state of nitrogen? +3. This one's called dinitrogen. What's 4? 4 is tetra, so dinitrogen tetroxide. Oxidation state of nitrogen? +4. And this would be called dinitrogen pentoxide. And the oxidation state on would be plus. Can we go any further than +5? No, we can't go any further. We got to stop here. And so we have +1, +2, +3, +4, +5. +3 and +5 are quite common, but that's maxed out. So those are the binary molecular compounds. And so what I'm going to do is you'll want to start memorizing those. I'm not going to quite finish chapter 3 today. So I just want to go back to the beginning of chapter 3 and let's take a look at identifying types of compounds. There's one more thing I'm going to have you memorize. Unfortunately. So we have molecular compounds. Molecular compounds are, they can be more than 2 elements. The molecular compounds typically are compounds formed from combining nonmetals. That's a rule. There are some exceptions. Do you know an exception to this? And so molecular compounds are going to be compounds of nonmetals. But there are some cations. Do you recognize this cation here? NH4 plus. What's that called? Did I give you this one to you to memorize already? This is ammonium ion. You need to memorize that. And so we could have something like ammonium chloride. Ammonium chloride is molecular or ionic? It's ionic. It's ionic because it consists of the ammonium cation with the chloride anion. And so that's an exception. So if this is a binary molecular compound, so we could just follow our rules. If we follow our rules, what would we call this? This would be called dihydrogen monoxide. Dihydrogen monoxide is often abbreviated DHMO. You heard of it? DHMO. There's a city in Orange County that came close to banning DHMO because of its potential toxicity. That is, if you have too much water, or it could be potentially fatal, right? Too much DHMO could be fatal. What's that?
Like how they treat you, you have to drink
Did you hear about that radio contest?
Yeah, they drink like gallons of water.
Yeah, they were drinking gallons of water, but you got to protect people
crazy.
from drinking too much. So, but it wasn't because of the radio; it was because of a prank, and so they almost banned it because of a prank. Still, fortunately, they didn't ban it, so everybody's still alive. There. Okay, we have other compounds, but these are not binary molecular compounds. So these are nonmetals, carbon, hydrogen, and oxygen. And when we look at this, this is a trinary molecular compound, and we don't have rules for those. So if you try to apply the rules for binary molecular compounds to a trinary, it doesn't work. So we don't call this monocarbon dihydrogen oxide. It doesn't work. And so for these are actually more complex. We'll talk about empirical molecular formulas later in this chapter, but for right now, to name these, we use organic nomenclature. And so this one is a weird way of writing this. I would not write this molecule here like this. And so don't write that like that. Write it like this. We write it HC2H3O2. Now do you recognize it? Yeah, acetic acid. And the reason we write it like this rather than this is to differentiate between these hydrogens. Let me make this bar. Acetic acid is what we call a monoprotic acid. Only one of the hydrogens is acidic. And this is the structure of acetic acid. Which hydrogen is it? And these black ones are carbon, the white ones are hydrogen, the red ones are oxygen. And so is it one of these three over here, or is it this one over here? It's this one over here. And so these ones we call non-acidic hydrogens. Those don't react in acid-base reactions. However, this one is an acidic hydrogen. That one reacts. So this one gives a little bit more structural information. And that little bit of extra structural information tells me that's an acid, having the hydrogen, the acidic hydrogen, separated out from everything else. Okay, so this is acetic acid. There's other ways of writing this, which gives even more information. So if I wanted a full representation of that, so this is the ball and stick model. This is what we call space filling model, the ball and stick. The sticks are missing here, so it's just molecular model space filling. Just balls for the atoms. And this is the Lewis structure here. And so these three structures can be condensed down to this, but we don't normally condense it down that far because we want to retain a little bit more structural information. And the little bit more structural information is like this. Do you see this CH3 here? We write that as CH3. So that would be this group here or this group here. That's the CH3. And then we have a C bonded to that. And then we have two oxygens. The two oxygens are, since we write in a line like this, we have to write them together. And so this gets confusing because this looks like a peroxide. It looks like an oxygen bonded to an oxygen, but it isn't. It's a carbon bonded to this oxygen up here, bonded to another oxygen over here. And so some people will write this CH3CO2H. Now the acidic hydrogen is on the right side of the formula rather than the left side. But this is probably one of the most common ways of writing acetic acid because it retains some structural information. Now the COOH group in organic, this is an organic molecule. Now the difference between organic carbon and inorganic carbon is organic carbon will typically have hydrogens bonded in there. And so if there are hydrogens bonded in there, then we know it's organic. And a lot of organic molecules are what we call electron-rich. I'm going to teach you another way of doing oxidation states based on Lewis structures later. But acetic acid, let me ask you this. Does acetic acid burn? No?
It does.
Or yes?
I think it doesn't.
You don't think it does? it burns. Acetic acid burns, actually. And that's because of the oxidation state. The oxidation state on this carbon, I'll show you how to get it later, but the oxidation state on this carbon is -3. If you have -3, you can go all the way to +4. So to go from -3 to +4 would be losing how many electrons? 7 electrons. And so if it has 7 electrons, it can give up, we call it electron rich. That's a lot of electrons it can give up. And when you burn acetic acid, do you know what it burns to? For example, like, do you like barbecue sauce? Or hot sauce? Or oil and vinegar dressing? You know, are those calorie-free? No, and you would think the calories not from the vinegar, but the calories are from vinegar as well, because you can burn this, and when you burn this in your body, you exhale CO2. I mean, you don't literally have flames, but you're essentially doing the same thing. You're oxidizing it, because we inhale what? We inhale oxygen, which is going to oxidize the acetic acid to CO2. Now, a lot of organics are electron rich. So one of the ones that are most electron rich is this. So CH4. What's the oxidation state? Now, if it comes carbon versus hydrogen, which one do we assign first? Carbon or hydrogen? So what the order is: group 1, group 2 metals, followed by fluorine, followed by hydrogen. And so we go hydrogen first. Hydrogen is going to be +1, and we have 4 of those. So 4 times +1 gives us +4. +4 plus what gives us 0? -4. So this carbon's at the negative end of the oxidation state spectrum. And so to go from the negative end to the positive end, we go from -4 to +4. How many electrons would we lose? If we went from -4 to +4, how many electrons is that? 8. And so this is what we call quite electron rich. And so if I'm, like, I used to have a motorcycle too one time, and if I'm following like a diesel bus, I used to hate it because of the fumes of the diesel bus. It would be bad. But you know, they have the CNG buses. Have you seen the CNG buses? Those burn a lot cleaner, because the CNG buses will burn methane, and methane's an excellent fuel. It's electron rich. So a lot of these organic compounds are on the negative end of the oxidation state spectrum, and a lot of them are flammable, organic. And then the inorganics are more on the positive end. And this is called an organic acid here, acetic acid. Here's some more organics here. When we look at organics, the first thing I look at in structure is I look at how many carbon atoms are in the chain. How many carbon atoms are in this chain? 4. And that gives me the parent name. You know what the parent name is on this? Bute. Bute means 4 carbons in a chain. And then the ane tells me something else. So this is butane. And this would be the ball and stick model. This would be the space filling model here. The space filling model, it's hard to see the angles, the bond angles. Okay, how many carbons in the chain here? 3. And if I see 3 carbons in the chain, like here, 1, 2, 3 carbons in the chain, then I call it prop. And so the parent chain is prop. But then I have this branch. How many carbons in this branch? 1. If I have 1 carbon, you know what I call it? Meth. And so this is called methyl because a CH3 is methyl, and CH4 is methane. And so CH3 methyl is attached to and this is methylpropane. Now, people use butane in lighters or for torches. People use propane, not methylpropane, but just regular propane. Regular propane, you take off this methyl group and replace it with a hydrogen, then you have regular propane. And they'll use regular propane in barbecues. So these are all examples of molecular compounds, but even though these are binary, we don't call this. This is a binary molecular compound, and we have 4 carbons and 10 hydrogens. So we wouldn't call this tetracarbon dehydride or decahydrogen tetracarbide. We wouldn't call it that. Instead, what we use is organic nomenclature for these. And so for these carbon, hydrogen containing organics, we use organic rules for naming. We're going to learn some of the organic rules in this class. And so the first thing you're going to learn are the names for the parent chain. And so let's go to that here. I need to blow this up so I can see. So these are the parent chain here. 1 carbon in the chain, meth. 2 carbons, F. 3 carbons, prop. 4 carbons, but. 5 carbons, pent. 6 carbons, hex. 7 carbons, hep. 8 carbons, oct. 9 carbons, none. 10 carbons, dec. And so just start memorizing these. As the first step to organic nomenclature. So organics are going to have a different set of naming rules. Let me go back to what I was looking at earlier. This is testosterone, and it's a big molecule. This is just one single molecule of testosterone. I was listening to a YouTube video. Arcade Jr. Is on some kind of testosterone replacement therapy. Have you heard of that? And I guess it's keeping him young. I mean, he looks in great shape. But this is it, testosterone. When we look at testosterone, it looks like a lot of hydrogen and carbons. When we see hydrogen and carbons, we call those hydrocarbons. So it looks like a lot of hydrocarbon here. But there's some other stuff here. There's a carbon, oxygen, hydrogen. When I see carbon, oxygen, hydrogen, I automatically think of what? I think of alcohols. And so we call this an organic functional group. And this is going to have some properties of an alcohol here. And then over here, this is a ketone where we have carbon, carbon, carbon with oxygen double bonded ketone. I think he's also on the fasting diet. And so he's trying to metabolize ketones rather than whatever. These color coding, it's hard to come up with so many different colors. But typically hydrogen's white, carbon's black, oxygen's red. The halogens are usually green. Not always. Nitrogen's typically blue. The other colors ignore. Actually, you don't bother memorizing these colors here, because they change. All right, those are molecular compounds, and those consist of discrete molecules, and those consist mostly of nonmetals. We have ionic compounds as well. Ionic compounds are mainly metal compounds of metals and nonmetals, or ammonium and some anion, or ammonium analog and some anion. And so one of the key differences is structural. When we're dealing with ionic compounds, it doesn't form discrete molecules. Instead, it forms this. What is this called? ionic lattice, or crystal lattice. And when we look at the crystal lattice, the simplest unit of a crystal lattice is called the formula unit. And you might think the formula unit is a molecule, but it isn't, because this purple is actually bonded to all these greens. And so, they just decided to pick this bottom green, but we could have easily picked the top green, so this purple is also bonded to this. And so what they're doing is they're just picking out one of these units. They could have picked this one out. This would be a formula unit. This would be a formula unit. This would be a formula unit. So there are lots of formula units. And so ionic compounds are going to have a different structure, and then we're going to also have network covalent. We'll talk about those more later. Okay, this is some more conversion factor calculations, the mole concept and chemical compounds. But what I'm going to do is, since I want to get more of the memorization stuff out, I want to go back to the organic nomenclature. And so we'll look at some organic nomenclature next. So how many carbons in this chain? 2. And then I see a COH. COH is an alcohol. And when I see an alcohol, then what I'm going to do is I'm going to take the chain name, F, and then I'm going to modify it, ane. Ane means there are no double bonds. They're all carbon-carbon single bonds in this chain. And the all means it's an alcohol. So this is called ethanol or ethyl alcohol. Ethyl would be the CH3CH2 group. CH3CH2 is called ethyl, and then we have the alcohol attached to that. This one's called methyl alcohol because we have a CH3 group. The CH3 group is called methyl. And, or it's called methanol. And then we have these alcohols here. How many carbons in this chain? 3, so it's prop. And then there are no double bonds here. And so it's ane. And then the alcohol. Now we have a choice here. We could stick the alcohol on the end, either the right end or the left end. If we stick it on the right end, we call it propane-1-all. That tells me that the alcohol is on carbon 1. But what if I put it on this one on the left? If I put it on this one on the left, then do I call it propane-3-all? No, because if I put it on the left, it depends on how you number it. You can number it in any direction. So we always pick the smallest number. So rather than calling this 3, we call this 1. We choose the lowest number. And so it doesn't matter where you start. We usually start numbering from what we call the functional group. Interesting. Okay, here, this is the alcohol stuck on the middle carbon. The middle carbon is carbon number 2. So it doesn't matter if we number this left to right or right to left. It's still going to be carbon 2. So this is going to be propane-2-all. Okay, there are other names for this. The common name for this is propyl because a CH3CH2CH2 is called a propyl group. A propyl group consists of a methyl group, and then a CH2 group is called a methylene group. So it's a methyl, methylene, and then this. Over here, this is called propane-2-all, or it's called isopropyl alcohol. Isopropyl alcohol has this little fish tail. That's called the isopropyl group. It's a propyl group where we bond to the middle carbon, not the end carbon. If we bond to the end carbon, then we just call it propyl. If we bond to the middle carbon, we call it isopropyl or 2. We're just going to kind of quickly go through some of these. I think the more examples that we see, the easier it is to remember this stuff. Okay, this is an alcohol, but this alcohol is slightly different because it has a carbon double bond to it. And so when we have a carbon double bond, this is the COOH group. COOH group or the CO2H group. This is called a carboxyl group. It's for the carboxylic acid group. So the carboxyl group is this for carboxylic acid. And so the simplest of the carboxylic acids is just going to have one carbon. And so one carbon, we call it meth. There are no carbon-carbon double bonds, so it's ene. If there were carbon-to-carbon double bond, we give it ene with an en. If there's a carbon-carbon triple bond, we call it ine with a yn. So it's either methane, methene, or methine, depending if they're carbon-carbon double or carbon-carbon triple bonds. With meth, we only have one carbon, so it's always going to be an ane. So it's going to be methane. And now we have this acid group attached, so we call it methanoic acid. Or the common name for this is formic acid. Formic acid is the acid that ants use. How many carbons in this chain? 2, so that's F. Are there any double bonds or triple bonds between the carbons? No, so it's an ane. Again, a double bond would be an ene. So ethene would have a double bond, ethine would have a triple bond. So it's ethanoic acid. Ethanoic acid. Ethanoic acid is also called acetic acid. And so we're going to look at more examples of this, but before we do that, let's look at hydrocarbons here. I went out of order, sorry, but I wanted to do those first. All right, how many carbons here? 1. Any double or triple bonds? Methane. So we just leave it at that. How many carbons? 2. F. Any double, triple bonds? Ethane. These are all highly flammable. 3 carbons here. Pro. No double, no triple bonds. Propane. So propane, this is what people use in barbecues. How many carbons here? 2. Double bond?
Yeah.
Yes. So now we change it. Ane, no double bond, no triple bonds. Ene means double bond. There's a double bond. There could also be single bonds, whatever. But this would be ethene. Or another name for this is ethylene, which consists of 2 methylene groups. The CH2 is called methylene. The 2 of those we did ethylene. This one has a common name. Sometimes we, there's other names for this. Another name for this would be cyclohexene, but we have 3 double bonds. So we would call it cyclohexene. 1-ene. So this is carbon 1, 2, 3, 3-ene, 4, 5. So it'd be 1, 3, 5 triene. That would be another name for this because it's cyclo, which means it's a ring of 6 carbons, hex. But that's too much. So instead of calling it cyclo hex 135 triene, we're going to call it benzene. So those are examples of what we call hydrocarbons. Hydrocarbons are compounds that only contain hydrogen and carbon. So we're dealing with 3 what we call functional groups, 3 types of structures. Structure 1 is just carbon and hydrogen, and there could be single, double, or triple bond. Structure 2 is alcohols with the carbon, oxygen, hydrogen. And the structure 3 would be carboxyl or carboxylic acids, and that would be the COH group. So start thinking about those, but get the numbers for the carbons down, and then look at these repeatedly. These are common organics here. All right, so we're out of time here, so I'll stop. Thanks.